When you multiply binomials that are the sum and difference of the same two terms, the product is the square of the first term minus the square of the second term. We call this the difference of squares because the product is just that, a difference of squares. Factoring the difference of two squares reverses the process to generate two binomials that are the sum and difference of the same two terms. Let's take a look. Is this binomial a difference of squares? It must meet the following criteria. Is the first term a perfect square? Well, x squared is the result of x being squared. Is the last term a perfect square? 16 is 4 squared, so it is. The last thing that we need to check is that this is a difference between these two squares. Since the three criteria for this binomial have been met, it classifies as a difference of squares, and we can move forward then with factoring this. So we've already established that x squared minus 4 is a difference of squares. We'll move then to where that came from with our factorization, the binomials having the same first and second terms, one being a sum and one being a difference on this term. So here we have it in factored form and our final result. It should be noted that when we have binomials multiplied together that have the same first and second term, but one being a sum and one being a difference, we have a name for this pair of binomials, and it's called conjugates. We'll see that numerous times in the future. Here's another example. Is this binomial a difference of squares? It must meet the following criteria. It's the first term a perfect square. Square root is 6x, so 6x quantity squared is equivalent to 36x squared. 81 square root is 9. 9, the quantity squared, is equal to 81. The third criteria, is this a difference? And since all three have been met, it is a difference of squares, which means we can factor this into the two binomials that have the same first and second term, one being a plus and one being a minus, with the square root of each of those original binomials that we have indicated here. Here we have another problem asking us if this is a difference of squares. Checking the criteria, the first term is a perfect square. 3 squared or multiplied by itself is 9. 16x to the 10th turns out 4x to the second squared. Also, that monomial squared is a 16x to the 10th power. Is it a difference? Sure enough, this is a difference of squares. Using our process as we've seen in the past then, with our factored terms of a square minus a square, we can then use the square root of the first and the second term to write our conjugate pair, square root of the first plus square root of the second term times the binomial square root of the first minus square root of the second term. Which one of these binomials is plus and which is minus? As long as we have one being positive and negative, everything is fine. And of course we'd want to multiply to check to see that we do have our original polynomial. Is this a difference of squares? We cannot forget that sometimes we need to factor out the largest common factor first. For this binomial, the largest common factor is 2x squared. Once we have it factored out, we'll look at the remaining binomial and ask the question, is it a difference of squares? First term, 5, quantity squared is 25. For our 4x to the 6th, 2x to the power of 3, that monomial squared is 4x to the 6th. It's a difference between the two, and so we will be able to factor our remaining polynomial after the factorization of the largest common factor. So moving forward with our factored trinomial or binomial here, 5 quantity squared for the first term and 2x to the third for our second term that's squared tells us our a and our b values for our conjugate pair. So the quantity 25 minus 4x to the 6 factors into these two binomials, same first and second terms, one a sum, one a difference. But before we're done, we have to be sure that we include that greatest common factor in our final answer for our complete factorization. Again, multiplying at any stage of your factorization should result in a product equal to what was originally given. Just a couple notes on working with factoring binomials. The first binomial on first inspection here looks like a difference of squares. The first and the second terms are perfect squares, but it's not a difference. It's a sum of squares. There is no general formula for factoring a sum of squares. The sum of squares is prime. You may be thinking, well, maybe it's x plus 8, the quantity squared. Well, if you take x plus 8 times the binomial x plus 8, we get an x squared plus 64, but the outside and inside, when we multiply the two binomials together, gives us a middle term of 16x. So this sum of squares cannot be factored into this form. You may think, well then how about put a minus in there? If you take the binomial x minus 8 times by itself, using the FOIL method and simplifying, we do get an x squared and we do get a 64, but again, the outside and inside when multiplying two binomials together, using the FOIL method, results in a middle term also of negative 16x. So neither one of these are the correct factorization for this sum of squares, and as I said a minute ago, sum of squares is prime. Just to take a look at one more time a difference of squares having the same first and second term, but the key being here the difference. This is factorable and factors into the conjugate pair of x minus 8 times the binomial x plus 8. On first inspection, this is a difference of squares because it meets the criteria of the first term being a perfect square, the second term being a perfect square, and it being a difference. So here we have our factorization for our difference of squares. Before leaving a factorization, it's always a good idea to inspect the results to see that they've been factored completely. Sometimes a complete factorization requires 2 or more steps. We see here the first binomial is a sum of squares. A sum of squares is prime, as we just saw. However, the second term highlighted here is another difference of squares. We can factor it with the conjugate pair being the square root of the first term and square root of the second, one being a minus and one being a plus. Anytime when you've factored and your results have a power greater than 1, you should be suspicious that you can possibly factor it further. Our sum of squares can't. It's prime. But the difference of squares from the original difference of squares can be factored further. Now we have a power of 1 on our x. There's no way that this can be broken down any further. The product of these three binomials will result in the original binomial that we started out with to factor. A difference of squares is not the square of the difference. Here we have a difference of squares, and we're noting that the square of a difference is not the same. A binomial to the second power means that binomial times itself. When we use the FOIL method, first terms is the x squared, last terms is a positive y squared, which already shows a disagreement, but we still have the outside and the inside to multiply for our binomial multiplication, which is generating this middle term. So this is certainly not the same as a difference of squares. A difference of squares will factor into square root of the first term, square root of the second, with a sum and a difference in each of the two binomials.